breakfast tacos, so help yourself in the few minutes during our transition to Alex's presentation. Thanks.
It was real.
Perfect. All right. Good morning, everyone. My name is Alec Forsman. I'm an employee at Advanced Space. And today I'm going to talk about a little bit about the projects we're working on to enable autonomous operations in space. So a little bit of background about Advanced Space. We're based out of Boulder, Colorado, and we exist to support the exploration, development, and settlement of space. And we do that through the variety of projects that we're working on. We do projects in many different realms of orbits. We have Earth orbiters, missions to and landing on the moon, deep space missions, and we do a lot of the mission design, trajectory optimization, low thrust optimization, systems engineering for these projects. Also working on a few satellite constellation projects, doing the planning and design for those. And then what I'm here to talk about today is spacecraft autonomy. And so we have three main projects right now working on doing autonomous operations in space. The first one is the Cislunar Autonomous Positioning System, or CAPS. And then we have the Linearized Lambert Solver for distributed space missions. And then the Sustained Low Altitude Lunar Orbital Mission, or SLALOM. So I'll talk a little bit about those. So first off is CAPS, and what CAPS is, it's a peer-to-peer autonomous navigation system to generate onboard navigation solutions using inter-spacecraft range and range rate measurements. So basically getting a state estimate of your spacecraft independent of Earth-based tracking stations. And not only can we do this for spacecraft, but there's the planned development for landers and rovers as well. So obviously this is focused more towards the moon. And we are currently integrating this as an application in the core flight software architecture, such that it can be easily integrated into different flight software architectures. And the goal of this is to create a self-sustaining, scalable constellation able to maintain its own navigation solution. So you can imagine this would work with two spacecraft, but as development to the moon continues, this can expand up to as many spacecraft that are participating. And it implements over a decade of algorithmic research, and we're implementing that finally in a flight software environment. And we're hoping we provide an innovation to a new way of doing navigation in the cislunar environment. Again, traditionally it's done using Earth-based tracking stations, and we want to kind of get away from that to reduce ground network congestion. And then we hope to redefine mission operations in that environment as well. So here's a more graphical overview of CAPS. In the top left, you have what's traditionally done today. So again, we have spacecraft in a variety of different orbits and communicating with the ground, and that the state estimate of the spacecraft is determined on the ground. And then we have the initial use of CAPS in the top right there. So we have a few spacecraft demonstrating the concept of CAPS, but there's no dedicated satellite in the CAPS network. So these are just customers doing their own mission and occasionally getting navigation updates between spacecraft. And we're currently working with partners right now for spacecraft in orbit to get this implemented, and also customers that are planning on launching spacecraft to the moon. So then, as you can imagine, as the system grows, we move to this expanded use, and we can support more diverse missions. And then finally, we hope to get to here where we enable the growth and operations in the cislunar environment. and when we can expand it to landers, rovers, as we move back towards the moon. So some preliminary results of this, just very simple. We've tested this in a lot of different scenarios. Here we have tracking between a low lunar orbiter on the left and a halo orbiter on the right. So here we're simulating inter-spacecraft range and range rate measurements, and then we do that using continuous tracking and then 2-hour tracking. So talk about the continuous tracking. You can see that after a couple days, we see that our state estimates, these are the 3 components of your position estimate. You see though we can we can estimate those down to about 10 meters for the low lunar orbiter. And then the halo orbiter, we can estimate down to about 100 meters of accuracy in position. And then similarly, for 2 hours of tracking per day, we're seeing similar numbers. It takes a little longer for us to get down to that same accuracy, but we're still getting down to about 10 meters after 5 days, and then for the halo orbiter down below 100 meters in position accuracy. So that's CAPS. Next, we have the linearized Lambert solver. And so what this is if you can imagine, you have a distributed space mission or a constellation of satellites, and then one of those satellites you would dedicate as your manager of the constellation. That's what we call it. And then that satellite determines the traditional Lambert solution, and that can be done on board or on the ground. Say you did it on the ground, you could upload that solution to that manager spacecraft, and then using the relative positioning of all of the other spacecraft in the constellation, determine a linearized Lambert solution at less than 1% of the computational cost of that traditional solution. And so again, we're also currently developing this as a core flight application. And what we hope to provide with that is simplified constellation management. As you can imagine, station keeping, maneuver planning, different mission operations for a constellation is obviously much more difficult than just doing it for a single satellite. So we hope that this solution can simplify that. You can also use it for initial onboard determination, and then more importantly, again, we hope it reduces ground station congestion. So you can imagine if you have a constellation, instead of communicating with all of the spacecraft in your constellation for this, you can just communicate with that manager spacecraft and be able to perform some of the same things. And through this, we hope to expand scientific and programmatic DSM benefits. So again, as I mentioned, we have been implementing this as a core flight application, and here is just some preliminary, very basic results from that. And through this implementation, we've been able to implement a core flight linear algebra library that we use for this, and we've successfully demonstrated it on more than 1,400 test cases. And we've automated those test cases to continually test our application. So on the left here, you can kind of see that. So this green dot is your manager spacecraft, and we're performing three maneuvers for each spacecraft, or 1 maneuver for each spacecraft, so 3 in total, to rearrange the constellation. This is just a simplified 3-satellite constellation. And then you can see the relative positioning of these spacecraft about the centralized manager. And then that's what we see on the right is you can see the position and velocity development of those spacecraft relative to that manager spacecraft. And then lastly, we have SLALOM, so the Sustained Low Altitude Lunar Orbital Mission. And what we hope to do with this is create a new orbit management system that combines several autonomous capabilities to kind of push the envelope of current GNC capabilities. And so this system, as we're developing it, must be able to detect and avoid surface features on the moon. The key word being avoid there. So relative to the reference radius of the moon, surface features are about as high as 10 kilometers on the moon. So we are proposing flying a mission of an altitude below 10 kilometers on the moon using this system. And this system is in very early development. And we hope that, well, it needs to be able to provide the spacecraft with navigation data, again, independent of Earth-based tracking systems. Because as you can imagine, at that low altitude, you're in constant, well, you won't be in constant contact with Earth. You need to know where you are and quickly be able to maneuver to avoid these surface features. So we're developing algorithms to fuse several navigation sources. While these aren't independent of Earth-based tracking stations, we're mainly focusing these on like laser altimetry data, so altitude, and then LiDAR for terrain relative navigation and surface feature recognition. And again, one of the constraints of this is some of the current capabilities of LiDAR. We're pushing the envelope at about 10 kilometers, and that's kind of why we're proposing flying at this low altitude. And a lot of this comes from using LRO data, specifically from LOLA, to kind of map the surface of the moon. It's kind of the most accurate map of the surface that we have to date. And using this, we're creating heuristics for efficient, effective maneuver planning and execution. And what we hope that this mission enables, a fundamental change to deep space mission, new ways to doing navigation, but also at this low altitude, we hope that we can enable new realms of science data at the moon. So those are the three main projects. For all of these projects, we recognize the need for a standardized flight software approach. I've mentioned CoreFlight a lot, and I know that was mentioned a lot yesterday as well. We also see the need and value for this as a standardized system. So we're excited about that. As you can imagine, CAPS and DSM would need to deploy these same algorithms over many different spacecraft and many different like architectures and environments. So the standardized system would help us ensure the integrity of our products across these many different environments. And as I've been mentioning, CAPS and DSM are currently in development as CFS applications, and the planned development for Slalom as a CFS application next year. And we're using this. We don't propose that we're writing an entire flight software system for a whole spacecraft. We're hoping that we can just use CoreFlight as a means to run alongside other customers' flight software for easy interface and access. So with the flight software development, we also understand the need for extensive testing on this. And so we are leveraging our astrodynamics expertise to develop a test bed for our flight software. And what we're hoping to achieve is using a variety of open source tools, integrate a system to simulate a full spacecraft. And so some of these tools that we're using are Johnson's Copernicus, Goddard's GMAT, JPL's Monty, and CU's Basilisk. And we get a variety of capabilities with this. Just to touch on it, Copernicus we can use for optimization. GMAT we can use for mission design, trajectory design. Monty we get orbit determination, and Basilisk we get attitude determination and control. And we're using these in addition to some of the internally specialized tools that we've developed, such as scheduling optimization. As you can imagine, scheduling tracking passes between all the different satellites for CAPS becomes a complex problem when you have hundreds of satellites in that constellation. We also have tools for interspacecraft communication and cloud deployment. And we're integrating some of these tools and centralizing them around CoreFlight such that we can test any of our custom applications. Kind of just drop it in there and turn on some of the things that you need and be able to fully test it on any platform. And through the early implementation of this, we've been able to demonstrate redefined CFS ground station to allow for facilitated integration in a project. We've also experimented with different messaging buses and serialization techniques to communicate with different, for interprocessor communication and to communicate with different CFS instances. I should note that we're using 6.5, so it's exciting for us to hear about the SBN and all of the good work that people have been doing with that. So we hope to get our hands on that and test that out. And then we've also experimented with interfacing with different programming languages for different advantages. Particularly, we've interfaced CFS with Rust, and I know Chris Robinson will talk more about that tomorrow in his presentation, so I won't go too much into that. So I think that's all I had. Did anyone have any questions?
Questions? For Alec? Thank you, Alec.